Hi AP Stats. We are going to take some notes on the rest of 11.1 today. So we're going to run through really quickly the things we've already learned. We started by introducing the chi-squared statistic by looking at our M&Ms. And remember, we were calculating the difference between what we observed and what we'd expect in a bag of M&Ms. So then we talked about our hypotheses, how often the hypothesis is going to be that a stated color distribution is accurate or true versus a stated distribution is inaccurate or not true. And then we calculate our chi-squared value, which is the sum of the observed minus expected squared all over the expected counts. The bigger that value is, the more evidence we have against the null, because that means our observed and expected are further away from one another. We looked at our chi-squared distribution, which is a distribution that is skewed to the right, has a degree of freedom equal to the number of categories minus 1. And then we looked at one example about a loaded or not loaded die. And we calculated a p-value, probability of our statistic happening, and talked about how it wasn't very unlikely that this would happen because there was a 64% chance of it happening. Thus, probably she has a fair die. So let's talk about carrying out a chi-squared goodness of fit test. This is our first test and the only test we're learning in this section. Just like with our significance test so far, we're going to talk about the 4 general steps our good old state plan, do, and conclude. And the state plan, do, and conclude are going to be very similar to what we've known so far. So in our state, we're going to list our hypotheses and a significance level. Remember, our null is going to be something like the stated distribution is correct, and the alternate will be the stated distribution is incorrect. As always, we want to give context and define any variables, though very likely you won't be defining any variables in this step. Also back up to our significance level, the most common, 5%, that doesn't change. Then we go to our plan. In our plan, we are going to list what inference method we are going to use. This is no different. And check conditions. So the inference method we are using, of course, is the chi-squared goodness of fit. I say of course because that is the only test we have talked about really so far. And our conditions are going to be very familiar, which is a good thing. If we think about what we know about our conditions for our previous significance tests, we had random, normal, and independent. But if we think about chi-squared, that graph was clearly not normal, right? It was skewed to the right. So we actually don't have the normal condition anymore. We are going to replace this normal condition with something called the large sample size. Now our random condition is just like we've seen, where we want a random sample. Our independent condition is just like we've seen. Our sample size is less than or equal to 1/10 of our population. But then what does this large sample size condition need? So this is the one that's a little different. Our large sample size condition can be checked by looking to see if all expected counts are at least 5. So if you have your M&M worksheet, you can go back and look through, see if there's any expected counts that are not 5 or more, and if that's true, then technically we couldn't have done any inference. However, it's very likely most of yours were at least 5. So really the only thing that's changing in our plan is one condition. State plan do. What do we need to do in the do step? Well, we're going to calculate a test statistic. And our test statistic for a chi-squared test is chi-squared itself, which remember is the sum of our observed minus expected squared all over expected. And we calculate this chi-squared value, and then what do we do with it? Whoops. Well, we take that and we find a p-value, or the probability that we would get this chi-squared value or more extreme. And our more extreme is always going to be greater than or equal to in our case. So whatever number we get here, whatever number we get as our chi-squared value, you're going to put that number, you're going to find the probability of this happening. Remember, we can find this in chi-squared CDF, which is in your calculator under the distribution, which is second vars. And we need to note that our degree of freedom is the number of categories minus 1. Once we have our p-value, our conclusion is the same. State plan do and conclude. Where we compare our p-value to alpha. If our p-value is less than our significance level, we reject our null, which says we have convincing evidence to say the alternate is true. And if our p-value is greater than our significance level, we fail to reject our null hypothesis. So realistically, looking at these state plan do and conclude, the main differences are that our test statistic is a chi-squared value now, not a t or a z, and that our normal condition is changed to the large sample size condition. But overall, not too different. Let's run a test together. According to the 2000 census, of all U.S. residents aged 20 and older, 19.1 are in their 20s, 21.5 are in their 30s, 21.1 are in their 40s, 15.5 are in their 50s, and 22.8 are 60 years or older. The table at the right shows the age distribution for a sample of U.S. residents aged 20 or older. Members of the sample were chosen by randomly dialing landline telephone numbers. The question is, do these data provide convincing evidence that the age distribution of people who answer the landline telephones is not the same as the age distribution of all U.S. residents? So here's what we know. This list right here is people who answer the phone. This is our observed values. These numbers are the expected percentages or the distribution of ages in the U.S. So how are we going to do this? Well, of course, we're going to start with our state. We would like to test the following hypotheses. At a 5% significance level, our null would be that the age distribution of people who answer a landline phone, age distribution of people who answer a landline is the same as the age distribution of U.S. adults. And our alternate would be that that is not true. The age distribution of people who answer a landline is not the same So I get to copy and paste, and I'm just going to change this to age distribution of people who answer a landline is not the same as the age distribution of US adults. We've got our null hypothesis, we've got our alternate hypothesis, I've got my significance level, I have a state. Next up is the plan. We will use a chi-squared goodness of fit test, assuming, and we need to check random, independent, and the large sample size. All right, let's do the easy ones. Random, let's go back up, just double check. Members of the sample were chosen by randomly dialing landline telephone numbers. All right. So I'm going to add that here. Randomly dialing. Oops. Independent. Our sample size is less than or equal to 1/10 of our population. Well, what was our sample size? 1,048. So 1,048, is that less than or equal to 1/10 of our population? Are there more than 10,480 US adults? Yes, there are. So we're good on independent. What about the large sample size? So for our large sample size condition, we need to calculate all of our expected counts. And so, okay, whatever. I wanted to make those things smaller, but this is okay too. All right, our large sample size. So here's what I know. I know that there's the 20 to 29 age group, 30 to 39, 40 to 49, 50 to 59, and then 60 plus. I know that the total number of people we sampled was 1,048, and the percentage of US adults who I would expect if I sampled 1,048, the number of US adults I would expect to be 20 to 29 would be whatever this number up here is, 19.1%. 19.1% of 1,048. So 0.191. And I'm getting 200.2. So we're going to do this for all of these. We would expect 1048. Oops. We would expect the number to be the same as the distribution above. So there were 21.5% in their 30s. So that means times 0.215. There was 21.1% in their 40s, so 0.211. There's 15.5% in their 50s, 0.155, and 22.8% 60 or above. So take some time to calculate these. If you want to pause the video, by all means do so. Couple notes. The first is, of course, I know I can't have 0.2 of a human being, but rounding to 1 decimal place is generally good. Oh, I'm so sorry. to give us a little bit more detail with our chi-squared value. That's piece number one. Piece number two is we should expect that all of these add up to 1048. So if you want to double check your work, that's a really good way to do this. And now look at what we've got. We check that all of these are greater than or equal to 5. Yes, they are. We have completed the large sample size condition. State, plan. Next up, we have the do. And I want to apologize ahead of time because I can't show you what I'm going to do in my calculator, but I will tell you to the best of my abilities. So in our do, we need to calculate our chi-squared value. Chi-squared, we know, is the sum of our observed minus expected squared all over expected. And so I'm going to write out one or two of these, but I am not, I want to stress this, not going to calculate this all by hand. We would start with our observed minus expected for the 20 to 29 age group. And so our observed in that group was 141 minus our expected, which was 200.2 squared all over the expected 200.2. And I'll write one more here just for emphasis, plus the 30 to 39 range. The observed was 186, yep, 186, minus the expected 225. All over that expected 225.3. But I would not, and I want to stress this, you do not need to write out all of them, nor should you be calculating them by hand. We are going to use our graphing calculators to do this. So I will talk you through what we're going to do, but I can't show you because I don't have the calculator function on this laptop. I apologize. But I'm going to start by plugging in my observed into list 1 and my expected into list 2. So I'll write the steps. You're going to click Stat. You're going to select Edit. We are going to put our observed into list 1 and our expected into list 2. We are now going to go to Stat Tests. Scroll over to Test. And we want the chi-squared GOF test. Chi-squared GOF. I believe on my calculator it is option D, so I'm thinking it would be yours as well. Chi-squared goodness of fit. And when I select that, it asks, hopefully it prompts you for observed and expected. If it doesn't, you would just type in list 1, comma, list 2, but it would ask for where did you put your observed, where did you put your expected, and then it asks for degree of freedom. And our degree of freedom in this case, there are 1, 2, 3, 4, 5 different categories. 5 minus 1 would be 4. So I put observed, list 1, expected, list 2, degree of freedom is 4, and I'm going to have that calculated, and hopefully you get the same thing that I got. I'm getting 48.22. Now here's what's really great about using our calculators. It gives us my p-value right away, so I don't even have to do the calculations. I basically just have to write down the work. So here's how we did this in our calculators. Now notice in my work here, I have shown the degree of freedom. That's an important piece. I have my chi-squared value, and then we're going to find the p-value, or the probability that I would get a chi-squared value that big or bigger. So greater than or equal to 48.22. Our calculator already spit it out for me. It says p is equal to 8.4857, a bunch of other numbers, e to the negative 10. What is that saying? Hold on, let's write this. 8.4, 8, 5, 7 times 10 to the negative 10th power. That means our p-value is almost 0, right? It's 0.00000, a lot of zeros, and then that decimal. All right. We have our test statistic, we have our p-value, state plan due. All we need to do is a conclusion. So our p-value, which is 0, is definitely less than alpha, which is 5%, which means we are going to reject our null hypothesis. We have convincing evidence. To suggest the age distribution of people who answer a landline is not the same as the age distribution of all US adults. Now think about this for a second. Hopefully that makes sense to you. Kind of makes sense to me. I don't think a lot of people maybe, in their 20s right now have a landline. I certainly do not. And so people who are answering a landline are very likely people who are older. So it makes sense that the people who are answering the phone are not going to be the same ages necessarily as all of the US adults. Join me next time for the second example in this section, and hopefully by then I can show you the calculator commands.